Okay, yeah, thank you very much. Yes, so I'll be talking about these breathing Kagome lattices, which have already been discussed here yesterday. So I think both in the case of molybdenum oxide and also niobium halides were discussed, but I'll focus only on the 2D variants of these. I mean, these are layered, but these are the pure 2D systems, which might be a little bit different. So it will be a little bit weird talk, I think, because it's first of all, it's preliminary results, and it's also a little bit negative because it will be a lot about what has been proposed that you will do, and I think that you cannot do. But I'll focus on first describing the magnetic ground state, and then I'll talk about the electronic band structure. There's been this proposal of non-reciprocity in the bands and ferrovalley coupling in these materials. And then finally, the possibility of ferroelectric or magnetic switching. So, as I said, this has this breathing Kagome structure, which means that it's not an exact Kagome lattice, but it's sort of distorted, meaning that we have some small triangles here and some big triangles here. I mean, if the triangles were the same size, then it would be a perfect Kagome lattice of niobium atoms. So niobium atoms are forming a completely planar structure, and then on both sides we have these halide atoms, which can be chlorine, bromine, or iodine. And so in this structure, it has the space group 3 and 1, so it's a polar space group, and it has a polar out-of-plane axis. So this definitely have an out-of-plane dipole moment. And then we can look at the band structure. Just the basic LDA calculation reveals that it has a band gap, and it's also a spin half system. So this can see just because we have one more occupied spin up state than spin down states. And the reason why it's a sort of an effective spin half system, although you have this niobium-3 cluster, has been explained in this paper, can be understood from the crystal field splitting of these 3 niobium atoms, which distributes like this, and we have one surplus of spin up, which makes this a spin half system. So these bands have also been investigated with strained RPA, dynamical mean field theory. And if you take one of these 2 bands and try to construct Wanyi functions, you'll find that it can be represented as a single Wanyi function, which is completely symmetric in the 3 niobium atoms. So all this points to these 3 niobium, this niobium cluster of the small triangle constitutes a single unit. And from a magnetic modeling point of view, we would think of this as a single spin half site in the unit cell. So even though it's as sort of a complicated stoichiometry, this is really a triangular spin half model from this point of view. And these flat bands have also been seen experimentally in ARPES, and there's been studies with the dynamical mean field theory. And there was also a recent paper here where they argued that this case of niobium chloride is sort of the ideal one band Hubbard model. It's very simple in this sense because it's just one Wanyi function you need, and then you have this nice Hubbard physics going on. But I mean, it seems like you get what you need from just plain DFT. But I mean, that's of course up for discussion. Now, one of the things that have been proposed in these materials, which makes them rather interesting, is this ferrovalley effect. And because we have this broken inversion symmetry, that means that if you include spin-orbit coupling in your band structure, then you actually break the degeneracy between K and minus K. I mean, everywhere in the Broglie zone. Of course, if you don't have spin-orbit coupling, then we have effective time inversion symmetry in both spin channels, and we would restore this reciprocity in the Broglie zone. But with spin-orbit coupling is broken, that means that you can actually access one specific value if you have a particular state of polarization, and if you reverse the polarization, then you can access another value. And you could imagine that each of these values would be accessible by polarized light of a specific polar state, and therefore you could sort of probe the polarization state by optical means, whether you have the band gap in this value or in the other value. So there's been a lot of interest in this, also because these materials appear to be ferroelectric. I mean, they're polar and they should be switchable, so you can actually switch the polarization state with an external electric field. Now, if we look at the magnetic ground state a little bit closer, we can see that the small niobium-3 cluster actually exhibits a little bit of canting when we include spin-orbit coupling. And this canting, so they would like to split up like this. And the canting is, of course, increasing when we increase the weight of the halide elements on the spin-orbit coupling and slices for the iodide system. So this is nice, doesn't have any direct influence on the band structure, but this is worth to have in mind for later. Now, if we want to investigate the magnetic structure a little bit closer and find the magnetic ground state, we need to allow for the spins in different unit cells pointing in different directions. And a rather general way of approaching this is through this generalized block theorem, where we simply impose boundary conditions on the magnetization, going from one unit cell to the next. The magnetization is allowed to rotate by a certain amount, encoded in the boundary conditions, and then we can do DFT calculations in the primitive unit cell with all types of boundary conditions to map out this energy as a function of ordering parameter Q. And I mean, for example, Q equal to 0, that would be the standard ferromagnetic state, where Q equal to K, that would be this one-third order where all spins are aligned by 120 degrees, and the endpoint would be sort of stripy antiferromagnetic. Now we see that since this is the minimum energy, this is actually the ground state of this system. And I should note that we're not imposing any constraints on the internal magnetization density of the spins in the unit cell. So we have these 3 niobium atoms in the primitive unit cell, and they just choose to align themselves, right? So the picture of this effective one-side spin-half triangular lattice is conserved, even if we have this, right? Because all the small triangles are sort of intra-collinear with each other. Okay, and we can also construct a square root 3 supercell that contains this type of order and do calculations with full spin-orbit coupling, and we still find that this is the ground state. So this is fine. So this is this effective spin-half lattice I'm talking about, if we consider each of these clusters as a spin-half state. Now, by the way, the bromide and iodide, they stay ferromagnetic. If we do the same for those materials, they will have a minimum at the gamma point. But I'll stick with this niobium chloride system for now. So now we can look at this ferrovalley effect a little bit closer. So this is the band structure in the ferromagnetic state. And so what I referred previously were other people's calculations. Now this is our calculations. And we find in agreement with other people have found that in the ferromagnetic state, we have this kind of valley splitting. It's also present in all the other bands, but it's just much more pronounced in this particular conduction band here. Okay, but now if we try to look at the band structure in the one-third ordered state, then of course we need to include spin-orbit coupling. We cannot do that with the generalized block theorem. So we do a supercell, square root 3, which contains the order. And then we can unfold the band structure to the primitive cell to compare with the ferromagnetic band structure, which is shown as the black lines here. So this is the unfolding is why all of this intensity varies. But what we see very clearly is that the ferrovalley splitting is completely gone in the helical state. It's not there. So we have the same energy here and here. And this is kind of interesting. It seems like we restore a symmetry that's broken by the ferromagnetic state, but it's restored by the helical state. But one can easily understand this if we look at the crystal symmetries. Particularly, we have a mirror symmetry, mx here. We have similar symmetries, I mean, here, but let's just focus on this one. This will take k to minus k, or the x component of k to the x component of k over here. Now, if we don't have spin-orbit coupling, we still have that symmetry, right? Because spin-orbit, then the spins doesn't care about the lattice. But if we have spin-orbit coupling, and the spins are aligned in the plane, which they are in this case, because the EC axis is out of plane, so they are aligned with the C axis, then this symmetry will actually flip the spin. So in order to have a symmetry, we need to combine this symmetry with time reversal. And that leaves k invariant. So we don't have any enforced degeneracy in that case. If the spins are aligned orthogonal to the mirror, then the spins do not flip. And we do have enforced degeneracy at k and minus k. And the helical state, we also have we also conserve this symmetry because this, I mean, we flip the spins, but this symmetry will return this state here. So we can understand that the general C at K and minus K are enforced in the helical state, but broken in the ferromagnetic state. And I think this is rather interesting. That first of all, it's a bit annoying if you're interested in ferrovalley coupling, because if the ground state is really this, then you don't have it. The effect is gone. But it's also interesting because it means that you can actually probe the magnetic order by ARPES, for example, by looking on whether or not you have reciprocity of the bands that will tell you if you are in one of these states or on these states here. Okay. So now I've killed the idea of ferrovalley switching in this material. I'll go on to argue that it's probably not a ferroelectric material at all. So it's clear that it's polar, so it's pyroelectric. So you can invert it and get a state with opposite polarization. And polarization is out of plane one direction, one way or the other. So the question is whether this can be switched. I mean, it doesn't look like it's a long way of going here to here. I mean, you just need to switch this Navier maximum a little bit down. And there should be a transition state where you have a perfect Kagome lattice, and which is in an inversion symmetric state, so you have zero polarization in that state. So we can define a breathing parameter, which is the ratio between the large triangle and small triangle. And then we can try to do an isoelastic band calculation to connect this state to this state. And doing this, we find a barrier. Other people have also done this, found similar barrier. And this is it's rather large, but if you look at it divided by the area of the unit cell, it's comparable to what you find in other ferroelectrics. So it's not unreasonable. You can actually do this switching. And now the idea of switching is that you have this energy along the breathing mode, or the breathing parameter. And now if you add an electric field that couples to the polarization, then you can actually, if this was a linear function, then you just shift this entire function by a linear function. And if the slope is large enough, at some point it will be all downhill, and you will switch from this state, for example, to this state by electric field. Now, as it turns out, if we actually try to calculate the polarization along the switching parameter, it looks a little bit weird. Well, first of all, we do encounter a metallic state close to the transition state. And this is not so nice for ferroelectric switching. I mean, usually it's forbidden to have metallic states along a switching path because it will screen the electric field. But in a 2D material, it might still be possible because it's out of plane polar, right? So even a 2D metal is very bad at screening out of plane electric fields. So you might actually still be able to switch this, although you have a metallic state here. But what is worse is that the polarization is not monotonous. It starts here, then it changes sign, and then it goes back to zero. So no matter what electric field you try to include, I mean, you go back to this. I mean, you want to include an electric field which raises this point, but then you will eventually lower this point and make it uphill once you cross the 0 point. So if the polarization profile looks like this, there's no way it can be switched with a homogeneous electric field. So this, we believe, is simply not possible in this material, although it looks promising. Right. But I don't want to be, I mean, there are some interesting things still about this material, because, I mean, this region here you can access with electric fields. You can drive it back and forth in this type of region. And so you can ask what happens to the magnetic state when you drive the system in this region. Because, I mean, in one polar state, it would look like this. I argue that in small triangles, this is effectively a single spin half side. But if you go to the other polar state, then the situation is reversed. And now you have a different trimer that constitutes the spin half sides. So something weird must go on. Right? There must be some transition between these two types of triangular lattices when you go from one state to the other one. And as I said, we cannot actually access the transition state, but there must be something going on when you move towards the transition state and you move towards the perfect Kagome lattice here. Okay, so we can now do our spin spiral calculations. And so are these lambdas, I mean, these are the equivalent to the deltas here, but we can now do the spin spiral calculation for different values of the breathing parameter. So starting here, that will be the blue line here, delta equal, or here, delta equal to 1. And then when you move closer and closer in, you see that the minimum is stable at k for some time. But then all of a sudden it will switch to another state here, which constitutes a long-range spin spiral. So this is essentially a first-order phase transition because it doesn't evolve smoothly. It really jumps from the k state to a finite incommensurate q. And then this simply evolves continuously to longer and longer spin spiral states until you reach the ferromagnetic state here. So the idea is that you could probably switch the magnetic state by an electric field, driving it towards this state. But I mean, it remains to be seen if that's actually possible. I mean, we can also look at the transition state, but what actually, okay, the transition state may not be accessible, but what would actually happen in the transition state is that we go from this state here at the polar state, this distorted Kagome lattice. When we go to the perfect Kagome lattice, you change your state, you get Q equal to 0 order, means that you have order in the primitive unit cell, but then you have this 120-degree order within the individual triangles, which are now perfect and of equal size. So that's what actually would happen. Okay, so to conclude, I mean, I think they have very interesting from a fundamental perspective. They have this ferrovalley effect, magnetic phase transitions, but the chloride member of this system actually has a different magnetic order than is often assumed, and I think cannot exhibit this ferrovalley effect. And the chloride system is the most studied one, to my knowledge. Yeah, so I think this ferroelectric switching is questionable in this system, but it still, yeah, it will remain to be seen what happens experimentally. Finally, I would like to acknowledge my postdoc, John Mangere, who did most of the work, and funding from the Velux Foundations. So thank you.